This is Rosen, section 8.2, um, solving linear homogeneous and non-homogeneous recurrence relations. Here we're looking at an example of a linear non-homogeneous recurrence relation, and it will have the situation where the characteristic equation has a root of 1 and the um, particular portion, or the non-homogeneous portion, has an exponential in 1, and how we deal with that. So we're going to notice this is in the problem of finding a closed form solution for the sum of the first n integers, and we'll express that as the recurrence relation, that is a1 equals 1. The sum of the first integer by itself is 1. These are non-negative integers. And a sub n is equal to a sub n minus 1 plus n. So my characteristic equation is r minus 1 equals 0, so r equals 1. And notice that my non-homogeneous portion has an implied 1 raised to the n, even though you can't see it. So that means that a n p, it would normally have the form of p1n plus p0, but because I have this a root of 1 and this exponential portion is 1, I've got to multiply the whole thing by n. And so that means it equals p1n squared plus p0n. And now we will proceed to insert this proposed particular solution into the homogeneous recurrence relation and solve for p1 and p0. So for a sub n, I'm going to have p1 n squared plus p0n equals p1 n minus 1 squared plus p0 times n minus 1, because they're evaluating it at a sub n minus 1, plus n. And I will expand the binomial there. p1 n squared plus p0 n equals p1 n squared minus p1 times 2n plus p1 plus p0. I'll distribute the p0 into that binomial, minus p0 plus n. Remember, I want to get this to be a polynomial in n set equal to 0, so I can set my coefficients to 0. And I'll start to subtract out from the left side, and I notice that p1 n squared will cancel p1 n squared there. p0 n cancels p0 n here, so I get 0 equals, and now I'll combine my factors of n and constants. I get 1 minus 2p1 times n plus p1 minus p0. And since this is a polynomial in n set equal to 0, for that to be true for all n, the coefficients have to be 0, so I'll set this equal to 0, and I get p1 equals 1/2. I set this equal to 0, and I get p1 equals p0 equals 1/2. And so I can write down my ANP is 1/2 n squared plus 1/2 n. And so now I can go to my third step and combine my solution. I get a sub n equals a sub n h plus a sub n p, and I never wrote down what a sub n h was, but this a sub n h is going to be alpha times 1 to the n, which is just alpha. So plus alpha. All right, and then, equals alpha plus n squared over 2 plus n over 2. And I have an initial condition that a sub 1 equals 1, so a sub 1 equals 1 equals alpha plus 1/2 plus 1/2. Well, that just means 1 is equal to alpha plus 1. That means alpha equals 0. So a sub n equals n squared over 2 plus n over 2. And that might be more familiar in the form of n times n plus 1 over 2. And by being careful about watching for the root of 1 and this implied 1 in my non-homogeneous portion, we're able to derive the well-known expression for the sum of the first n positive integers.